Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Phil Bernstein. It's a pleasure to be introducing Alvin Chung today. Alvin is nearly done with a PhD at MIT and working on problems related to both databases and program analysis and program synthesis. At least part of the work he's describing here was the subject of a paper that got the Best Paper Award at the Conference on Innovative Database Research, CIDR, in January this year. And he's the winner of multiple fellowships, competitive fellowships, NSF, Intel, and National Defense Science and Engineering, which is actually
something like that.
Something like that, which is actually a very competitive program run by DoD. I think there's a total of under 200 fellowships that are awarded to in all science and engineering fields. And Alvin will be spending the day talking to a number of you. If you're not on the schedule and you want to be, let me know. Maybe we can double you up with one of the other meetings, or talk to him briefly at the end of the day. With that, let me give the microphone to Alvin.
Great, thanks a lot. So so I'm Alvin. I am, I guess by now, like an nth year grad student at MIT. N is basically like a number that I try not to remember. I guess the proper term, they call it a tenured grad student. I'll let you figure out what that really means.
A tenured. N plus 1 is when you get your degree.
Yeah, hopefully. I hope like the count would basically stop counting with N plus 1, right? So thanks a lot for the invitation today. So actually, originally I was thinking of giving like a 30-minute talk of some of the work that we just presented at PLDI this past week. But since Phil was kind enough to actually give me an hour slot, so I decided to change the topic a little bit to talk about a broader piece of work that we have been working on with multiple people that I have the pleasure of being involved with. So the general setting is that we're basically trying to use various program analysis techniques to speed up applications that uses a persistent data storage. And this is joint work with a bunch of folks at MIT and also Cornell. So to begin, let's just first review a little bit about like how these applications tend to be written. So in the original case, we have two servers, one hosting a database, in this case maybe SQL, and another one that is hosting the application server. So these two machines tend to be different physical machines, although they tend to reside in the same machine room for that matter. So these applications tend to be written using, first of all, a high-level imperative logic, programming language, if you will, a general purpose one, for instance, Java or Python. And embedded within these applications will be SQL queries that gets executed on the database during when the application runs. So at some point in time, people figure out like one way to speed things up is perhaps to carve out part of the application logic into what is known as stored procedures. I'm sure all of you in the audience are familiar with that concept. So there's something wrong with this picture, unfortunately. Well, so first of all, the developer needs to commit to either a SQL or imperative code during development time, not to mention that he also has to learn like what PL/SQL and all that stuff is all about. And as you can imagine, getting that wrong can have a drastic performance impact. And on the other hand, they also need to worry about how or where is the application going to be executed. As I've shown you, putting things onto the database server as stored procedures will make the application run as at least the half of it that is in stored procedure representation to be on the database, and everything else will be on the app server. So being able to make these two choices tends to be a little bit difficult, at least during development time, because things can change. Things can either both in terms of the application logic and also the state of the database, and making these decisions tend to be difficult. So in this respect, we try to use program analysis to help us solve these problems. So with that in mind, we started a new project called Status Quo funky name, I guess, which is a programming framework with two very simple tenets in mind. So first of all, we want to be able to allow the developers to express application logic in whatever way that they are interested or comfortable with. And with that regard, we think that it should be the compiler or the runtime's job to figure out the most efficient implementation of a piece of application logic. So notice that we're not coming up with some new programming paradigm or new programming language and ask people to please convert all your legacy applications into that. So on the contrary, we're basically saying that you should be able to write whatever you will, be lazy, just do whatever you want, and then we will basically do all the difficult lifting for you. So to kind of, as a first step to achieve this vision, we have developed two key technologies. So first, we have a piece of tool that will automatically infer SQL queries from imperative code. And secondly, we also have a piece of technology that will automatically migrate computation between the two servers for optimal performance. And I'm going to talk a little bit about these two pieces in this talk today. So first of all, let's just look at the first piece of technology here, which is we're trying to convert things from imperative code into queries. How does this work? Well, so here, what I've shown you is a piece of code snippet from a real-world open source application that uses some sort of ORM or object-relational mapping library for persistent data manipulation. So in this case, what we have here is that this person uses a third-party library which basically abstracts out all these things about users and roles. And then he's basically calling these functions to return a list of users and roles from some place. And then he then goes on in a nested loop fashion to filter out the ones that he's interested in and finally returning it at the end, right? So unfortunately, what he didn't know about is the fact that these two functions in the beginning, when executed, they're actually issuing SQL queries against the database in order to get back the list of results that he ended up looping across. And so what happens during execution is that when the outer loop is encountered, the third-party library, in this case the ORM library, is going to issue a select star query, because that's what this particular code snippet is trying to do. And likewise, when the inner loop is encountered. Now, as database people, when we look at this, we basically say, well, I mean, this looks very much like a relational join, right? So in order to speed things up, one thing that you might want to do is to just convert this entire code snippet into a very simple join query that basically folds in this predicate into the query itself. So the benefit is obvious, right? Because when we execute these two select star queries, when the database gets large, the application can slow down substantially. Whereas if we try to write it as a simple query, for instance, in this case, we ended up having orders of magnitude performance difference. So our goal in this case is to basically try to do this conversion from here to here automatically. So at this point, you should probably be, calling me out and saying, there's just no way you can possibly do this. I mean, look at this thing. It's like in a declarative SQL language. This thing is in imperative Java. Look at the differences between these two. It's pretty dramatic, right? So how can we actually pull this off? Well, so just to recap, what we're trying to do here, formally speaking, is to find a variable. In this case, results. We call that an output variable. And our goal is to basically try to rewrite this into a SQL expression. And we are going to basically do this using a tool that we just built called Query by Synthesis, or QBS for short. So this tool does three things, right? So first of all, we try to identify the potential code fragments that we can possibly convert into SQL queries. And secondly, for all these, what I was referring to as output variables, we try to find SQL expressions for them that we can convert them into. And finally, being a good programming language person, I would try we should try to at least show that whatever SQL expressions that we ended up finding, we better preserve the original semantics of the program. And if that works, then we'll go ahead and convert the code, right? So what do I mean by try to prove these things preserve semantics? It gets into a little bit of background in terms of program verification. But before I do that, can I get a show of hands? Like, how many of you are already familiar with OR logic, program style, verification? Okay, well, okay, yeah.
There was work on object-oriented programming languages which have loops, and how do you take that and make those joins in OQL context? Because this seems, at a high level, the problem looks very familiar.
Yeah, but except that in this case, from the user's point of view, he's not sure what's really going on in here, right? So it doesn't know that's what the actual code ended up doing, or the underlying implementation of the library. So this is for modularity reasons, right? So the guy who wrote this code might not be the person who developed these libraries. And when someone who wrote these libraries, he cannot possibly imagine how the result set that he actually ended up returning will get used. So in that respect, we're basically, so you can imagine these guys can be implemented using some sort of OQL, for instance. But then from that respect, we still need to somehow be able to fold all these things into the object query language itself in order to get the performance. Otherwise, all we ended up doing is just fetching everything from the database and then doing the nested loop. So that's not so efficient, as you can imagine. Okay, so just a little bit of background in program verification. So in this case, we use Hoare logic, which basically comes in this form, right? So this is a standard way of presenting this. So we have some sort of command that we want to try to prove. In terms of a state transformation, so we have a precondition that we know is true before this command was executed, and then we have some post-condition that we're trying to enforce after the command is executed in terms of changing program state. So as an example, imagine we have a statement that simple assignment, and then we want to show that x is less than 10 afterwards. So we can go backwards in terms of figuring out what must be true before this statement is executed in order to allow us to say that x is less than 10 afterwards, right? So of course, in this case, it better be the case that a is less than 10. So a more complicated example, what if we have a if-then-else statement in this case? So let's say we are also trying to enforce, somehow we are asserting the fact that x is also less than 10 afterwards. So what needs to be true before this whole statement gets executed? Well, in this case, it better be the case that if b is true, meaning that we do get into the if clause, it better be the case that a was less than 10. Or the fact that if b is not true, meaning that we'll go to the else branch, c in this case is less than 10. So there's a very routine automatic process of coming up with what is known as a verification condition given a post condition that we're trying to enforce. Okay, so for loops, it's a little bit tricky. So let's say in this case we want to enforce the fact that we want to show that somehow in this case sum is equal to 10. I mean, we all know, of course, this is true. So, but what is the kind of condition or verification condition that we need in order to establish that fact from the beginning of the program? Well, so it involves this magic thing called a loop invariance, which, of course, as we all know, means something that is true during the execution of the loop. So in this case, suppose someone has come up with this invariant that says sum is always less than or equal to 0 during the loop. So with that in mind, we need to be able to establish 3 facts about this program. So first of all, we need to be able to show that this invariant is true when the loop was first entered. In this case, it is, because we know that sum was set to 0. And that, of course, implies that it's less than or equal to 10. So we also need to show that this invariant is preserved, meaning that if we actually go into the loop and we go through one iteration, the invariant better be preserved, meaning that it still remains true, right? So in this case, we have if sum is less than 10, and the fact that this is the invariant, it better implies the invariant back. So in this case, this is also trivial, so it checks. And finally, we want to show that if this loop, we ever get out of this loop, then the post condition, whatever that we are trying to prove, we can establish that fact given the invariant. So in this case, we want to basically show that if sum is greater than or equal to 0, meaning that we break out of the loop, and given the loop invariant, we have sum is equal to 10, which is the post condition that we are trying to establish. So in this case, you can also see that this kind of also checks out because, right? I mean, basically comes up with the only possibility is that sum is equal to 10. Okay. So this is just a very tiny, very short introduction to program verification. Then what does that have to do with us, right? Well, so if you look back into this example here, what we are trying to establish, as I was talking earlier, in terms of these output variable, is the fact that this results variable better be equal to some SQL expression, right? So this SQL expression is precisely the post condition that we're looking for. Except that, and as I've shown you earlier, in terms of loops, what we need to do in order to establish this post condition is the fact that we need some invariance for these loops. Okay? In this case, we have 2 loops, so there better be 2 different invariants. So, and given all that, we can automatically generate all these verification conditions like the ones that I've just shown you in the earlier slide. Yes, question?
It seems that you should also make some assumptions that like no other module is modifying the database in parallel, right? Because in principle, I can imagine that someone else is modifying the users and then you just somehow informed to this program by some other signal, which is why we can't rewrite this as a join because that would mean completely different.
Exactly.
So what kind of assumptions do you make?
So in this case, so for many of these third-party libraries, they can mark things as transactional, which is what happens in this case. I mean, this whole thing is basically sitting in a transaction.
The entire thing is within one transaction.
Yeah. So, so getting back to this, so basically what we ended up doing is now you can basically see that we can automatically compute these sort of verification conditions that help us establish the fact that results equals to some post condition. Except that there's one problem in this case, right? So I haven't really told you what are all these invariants and what are all these post conditions. I mean, these are things that we're trying to look for, right? And at this point, we don't really know. Well, but as good computer scientists, what do, right? We just throw abstractions to the problem and somehow it will go away, right? So what happens in this case is we just say at this point that these guys are just some function calls. We don't know what the body of these function calls are, but we just say, okay, here are some invariant function that is a function of everything, all the variables that are currently in scope, and then we'll just leave it out for now and see what happens later on, right? Yes, question.
So how do you find these output variables? I think that's a pretty tough problem because as soon as you have something like C with pointers stuff, then I imagine that this is nearly impossible, isn't it?
So we actually run a bunch of analysis to figure out that, and I have a slide to talk about that. So hold on to your question. If I don't understand, if I don't answer that again, then please come find it, right? Yeah, so that's a very good point. So how do we actually figure out like what are the things that we can possibly translate, right? So we'll get to that in a second. Okay, so I was talking about, okay, so we basically treat these guys as some sort of function calls that we don't know how to express, right? But before I talk about like how do we actually generate the bodies of these functions, we first need to understand that all these things are actually written in some language that is used to express these kind of logical expressions, right? Because you see there's some AND thing, some implication thing. So we need to be able to have some sort of language for us to represent all these verification conditions. I mean, notice that this is not like Java, right? This is not like the original program. This is really a logical language. And in the previous slide that I've shown you for the simple examples, which involve things like integers and simple variables, we can just use very standard logical language for that purpose. But in this case, it involves like nasty stuff like queries and result sets and all that. So we actually need to talk a little bit about what is the language for us to express these kind of things, right? So as I was saying, whatever this language that we ended up using, it better be able for us to express all these verification conditions for the imperative code, or in this, which is the source language in our case, right? And more importantly, we need to be able to handle all these query operations that happen in the code, right? Because the code that we're dealing with has like queries embedded within the code itself, right? So whatever language that we use, we better be able to express all the relational operations. And in particular, the order of records actually matter. So that might come a little bit as a surprise, but if you recall like the nested loop example that I shown you earlier, there's actually an ordering of all the tuples that come out from that nested loop. And the ordering is basically based on what the database decided to return. So but unfortunately, SQL itself does not enforce a particular ordering unless we put in an order by clause, right? So in order to preserve the semantics of the original program, we somehow need to capture the fact that the stuff that is coming out actually has an ordering embedded within it. So whatever language that we use to represent these verification conditions, it better be the case that they preserve the ordering. So finally, we also want any post-condition expressions that we actually come up with is able to translate to the query language that we have in mind. In this case, the target is SQL. And finally, it better be the case that the function bodies that I told you, kind of like a mystery, you better be able to come up with what they are. Otherwise, we cannot establish the fact and do the kind of conversions, right? So what we ended up doing is use something called ordered relations, which is very similar to relational algebra, and with one caveat, which is that the relations themselves, rather than modeling them as bags of tuples, we actually model them as an ordered list. So what do I mean, right? So we basically mean the following. Here are some examples. We say that in this world, a query result set is an ordered list, and a list we can construct that by either setting that to some program variable where it's basically a query, or we can construct that by concatenating multiple lists together or concatenating with an expression. And along with, so these are basically standard list operations that most people are familiar with. But besides that, we also included a bunch of database operations that can operate on these lists. For instance, we say that we can do joins, we can do selections on these lists, which return other lists. And this top thing is basically the familiar limit clause that we have in SQL. So in this case, it basically returns the top I elements from this list, where I is the result of evaluating whatever this expression E is.
This colon is concatenation?
Yes, colon is concatenation. So I'm kind of overloading this a little bit here. These are actually concatenating two lists versus this is just appending something. So for expressions is what you would expect. So for instance, we can get something out of a list. We can do some operation on two elements of a list, and then along with that, we also define a bunch of aggregate operations that can return a scalar result, right? Okay, so now we have some sort of we have a language where we can express all these. Yes.
Why is order important? Because if you take the original SQL application, I run the same application twice, I might get different order. So there's no equivalence even between multiple invocations of the same program. Why do you try and have to preserve equivalence with order?
Yeah, because the ordering of the tuples can be arbitrary from the point of result, from the point of the result set being fetched from the database.
But I'm saying the application shouldn't care, because even if I run the application twice, the database can give it in completely different order, technically. Because the SQL language doesn't give you any guarantee about ordering.
Yeah, so
the original application is fine with different ordering across even invocations. Why should you care about it?
Yeah, that's because we cannot really enforce that, right? So in fact, we have seen applications where they do rely on the things that the ordering of the stuff that is relied.
They should use explicit order by clause if order is important.
Well, so in that case, for instance, the nested loop example, right? So they know that the underlying database can return the ordering of the tuples however they want, but then we know that whatever the first tuple that gets returned will then be joined in an inner loop fashion with everything else, right? So there's some implicit guarantee as to what the result set would look like if anything comes out of it. You kind of see what I'm saying? So because they have explicitly written a nested loop, right? So then the first tuple that gets fetched from the outer loop, whatever it is, will be joined across with everything else in the inner loop, right? Followed by the second tuple, so on and so forth. So there is some implicit ordering that we don't know whether that's really what the developer has in mind when he wrote that piece of code.
For instance, that example, you can enforce using hints. You can write a query with a join and you say enforce the order of the join.
Yeah.
That would take care of that example.
Yeah, exactly. So that's why we ended up doing this. And since we have to be conservative, we have to preserve the ordering of things. But I agree. I mean, for simple selection, it doesn't really matter, right? Okay, so now I'm basically left you with this kind of mystery where how do we actually generate these post conditions and invariants? And for that purpose, we pull out this magic box called program synthesis. So you can basically think of this as a search engine over the space of all possible SQL expressions, right? So how it works is the following. So given a program synthesizer, which is a piece of code or a basically off-the-shelf tool, we give it a symbolic description of the search space. So search space, in this case, being the space of all possible SQL expressions that we can generate. And we will also give as input a set of constraints that we want the synthesizer to respect. So guess what, right? So this set of constraints, in this case, is exactly the verification conditions that we have automatically come up with. So given these two things, what the synthesizer would do is it would do some sort of a search procedure, intelligent one, using a symbolic manipulation and what is known as counterexample-driven search. What does that mean, right? So that means we try to come up with an expression that, a candidate expression that can possibly fulfill the requirements that we want, meaning that it's able to satisfy all the verification conditions, and we try it out in terms of proving whether that's correct. And if that works out, then we're good. If not, then it incorporates that as a counterexample, meaning that, well, you better not return this same expression again, right? So that's kind of at a higher level how this loop or counterexample-driven search works. So hopefully at the end we'll get some example, we'll get an expression that satisfies all the constraints. Or in this case, what happens, back to this example, we would basically want the synthesizer to come up with expressions for both the post condition and also all these invariants, right? And to just give you a sense of how this works, in this case, let's say we're talking about the post condition, the synthesizer will give, as a description of the search space, right, a bunch of expressions, meaning something like this. So for instance, we might try to infer that results equals to some selection of the users list, some top, limit expression, or some more complicated thing, so on and so forth. And of course, we don't really write all these out explicitly because that would take forever. So we actually have a symbolic encoding of this search space. And because of time, I will kind of not talk about this. But if you're interested, please come talk to me afterwards. Okay. So finally, so now you understand how we actually do this kind of transformation, right? So it's an iterative loop where we try to find these expressions, and if it all works out, then we go ahead and transform the program. But as being pointed out, we need to talk about how we actually identify these code fragments to begin with. So very simply, we can just question.
It seems to me that you should also somehow model constraints like primary keys, uniqueness, which are there in the databases, because that can influence. It can kind of limit the space of expressions that we need to consider. So
exactly. So I skip a lot of details about how we actually efficiently encode the space of things and all that. But that's actually one of the things that we looked at. Okay. So for one thing, we probably want to start at where the code is actually fetching stuff from the database as a starting point, right? Because we don't want to deal with all these other things that parts of the program that actually does not involve any database operations. Okay, so that's the starting point of where we want to look for these kind of code fragments, and then we run a point analysis in order to figure out where things escape in terms of passing on to things that we don't know what's happening. So given these two information, this is actually sufficient for us to actually determine where do these persistent data, meaning that stuff from the database, actually flow to in terms of the program. And that, in turn, allows us to delimit the start and the end of these code fragments that we try to analyze. Okay? So these are actually very standard program analysis techniques that basically, we just have to do a lot of engineering to actually get to. But to summarize this part of the talk, so this is the way that this whole toolchain works, right? So it takes in the source code of the application unmodified, and we'll then try to find all these places that uses query results from the database. And then we'll try to find all these code snippets using the mechanism that I just talked to you about. And we'll end it up in something like, we'll be able to identify a bunch of code fragments within the original application source that we can try to do these kind of analysis and conversions. And given that, it will go through some sort of verification condition computation to generate the kind of logical expressions that we try to enforce. And then we'll try to do the synthesis step to try to come up with SQL expressions. And if that all checks out, then we'll go ahead and convert the code and put it back into the original application source code. And this thing, as I've shown you in the earlier example, is interprocedural. So meaning that we do look into different method calls and all that stuff. And so this is the entire toolchain. And now let's talk about a little bit, does it actually work, right? So the experiments we set up in the following manner. So first of all, we understand that there's no standard benchmarks available for these kind of transformations. I mean, there are some ORM libraries, there are a lot of open source applications, but there's no standard benchmark available. So we did our best in terms of finding 2 large-scale open source web applications for this purpose. In this case, these applications were written in Java using Hibernate as the ORM library. So we want to measure 2 things to test out our tool. First of all, we want to know how many code fragments we're actually able to identify and convert out of the application source code. And secondly, we also want to measure what is the benefit that we get in terms of execution runtime. Do we actually get any speed up in terms of converting things into SQL, right? Okay. So for the first part, so here is one application that we looked at. And I've basically broken this thing down into the types of different operations that we were able to identify in terms of the code snippet, and also the number that we were able to convert as a result. So you can see that we do we were able to convert quite a large portion of them. And they do come in a variety of different types of SQL operations, right? Joins and projections, whatnot. And here's another one, a similar story. So now in terms of performance, what actually happens, right? So now we start to measure what is the effect of conversion in terms of execution runtime. So on the right here, we have taken one piece of code snippet that we were able to transform. In this case, we transformed that into a simple selection query. The original application just fetches everything from the database and then do a filtering in a loop fashion and then return a subset of the result. So in this case, we try out with 10% selectivity, and then we try to scale up the size of the database to see and measure the time that it takes to load up the entire page, not just running the queries, right? So this is both fetching the stuff from the database and also rendering everything, getting the whole thing from the web server and displaying it onto the screen. So this is the original application, the time that it takes, and as I've mentioned, it basically fetches everything from the database, right? And here is what happens when we try to convert it into a single selection query. So you can see this is basically an order of magnitude difference, right? And it's pretty obvious because we're basically fetching a subset of the things as opposed to the original application that fetches everything and then doing filtering inside the application itself. So now we also try it with 50% selectivity. So again, this is the original application, and in this case, we didn't scale as good because obviously this is because the application was fetching more stuff than 10% selectivity, so we wouldn't expect the same kind of performance benefit, but you can still see quite substantial difference in terms of the time. Now, the more interesting case is actually the nested loop example that I showed you earlier, right? So this is the exact code snippet that I just shown you. So here's how the original application did. Not so hot. As you can see, this is basically scaling up n squared because this is doing a nested loop, right? And guess what? We actually ended up scaling linearly because we were able to convert from a nested loop join into a hash join because turns out that the database already has indexes for these tables. So just by converting into a SQL query, we magically get this kind of speed up, which is kind of good. And finally, same thing for aggregation, right? So in this case, this guy is trying to do a count. So he fetches everything, and then he basically sums up the number of tuples that he returned. And this is the original performance, and again we have another order of magnitude difference just by converting things into an aggregation and executing that inside a database, right? So just very briefly, I also want to touch a little bit upon what are the things that we actually fail to convert, right? Because as I've shown you earlier, we were not able to convert everything. So why is that the case, right? So first of all, there's like a bunch of cases where they use some sort of custom logic to do comparison. So for instance, they wrote their own comparison operator that compares some sort of string value out of the database and then sort the result set that way. So in that case, since at this point, at least in this initial prototype, we don't handle store procedures. So those kind of expressions we're not able to express in standard SQL. So therefore, we fail to convert that kind of thing. And another set of things uses database schema information. So these are the kind of more interesting cases. For instance, in this case, this guy is basically issuing a query that fetches things from the database, and it turns out that ID is the primary key, right? And then he decides to sort things out, and then he decides to get do this kind of loop. So look at this carefully. This is really just getting the first 10 elements from the table. But unfortunately, we're not able to convert this into the SQL representation because we didn't know that ID is the primary key, and therefore this is really the equivalent query in this case, right? So of course, if we incorporate that information into our prototype, we should be able to do better. But then that's basically future work at this one. Yes.
So did you find that you generated queries which turned out to make the app slower? That never happened.
At least in all the experiments that we've run, we have not encountered that case, and that's because things that we convert are things like selections or projections or joins. So unless the database implementation actually ends up slower than what the application source code already written, otherwise yeah. But that's a good question actually. So okay. So now we just talked about this this thing about converting things automatically converting things from Java to SQL. But as I've mentioned to you in the first part of the talk, we are still left with the problem of how do we actually execute the application itself, right? So because as I was saying, some part of it we can convert into SQL/store procedures, but then how do we make the decision as to when do we actually do the conversion, right? Okay. Again, the high-level goal here is to be able to be flexible in terms of how to execute a piece of code, right? Okay. So for this part of the talk, yes.
Before you move ahead, if you have nested loops in the application program and there's imperative logic in between the nesting, are there cases where that's going to cause trouble in terms of reverse engineering a query just because of the expressiveness of the query language when you get if statements and procedure calls and whatnot?
Yeah, that's a good question. So, so the classic example that we have seen, for instance, are basically people putting log statements inside the loop. So somehow you want to print out something like progress report. I have fed process out 50%. So for those kind of things, unfortunately, we cannot reverse engineer because we cannot put the print statement.
Well, but you're not also going to bring back all the data.
Yeah, exactly.
In the outer loop.
Exactly. So I mean, the fortunate thing is we can indeed detect those cases and bail out of it. So we are sound in that purpose. Yes.
Can you partially convert? So for instance, you have that application logic or something like you need to return a list based on a table, and you need to filter out the ones where the numbers in a certain field are prime or not. And so you can certainly propagate that logic, I'm sure, to the SQL, but then can you kind of separate that logic to do another filter within the application language, or does it kind of fail on an instance like that?
Yeah, so for now we decided to bail out on that particular case as well. But yeah, I think that's an interesting point where we can actually try to, but then that also gets into the question of how much we want to convert, even though if we can, I mean, we don't have to convert everything, and that's actually part of this second half of the talk. So that's a very good lead-in, actually. Okay, so now we want to talk about where we want to execute a piece of application logic, right? So as a running example, I'm going to use this code fragment, which is all familiar with TPCC. So in this case, this guy is trying to basically do some sort of a new order transaction. So as you can see here, what happens is that initially we execute some sort of query, and then we compute some sort of total amount, and then we do an update into the database, so on and so forth. So notice that when we actually execute this piece of code, what's going to happen is that the first statement is going to be executed on the database, right? Because this is a query. Okay. So, but then the second line is going to execute on the app server because this is a piece of imperative application logic, and so on and so forth for the rest of the program. Okay. So notice also because of this that we actually get some network communication between two statements because either the database has to relay the result set back to the application server, or the application server has to tell the database, okay, please execute this query, right? And in this particular example, there turns out to be quite a lot of these network communication, or network round trip between the two servers. And these ones, again, turns out to be not so good in terms of performance, right? It slows things down. So in this case, our goal is to basically try to eliminate some of these round trip between the two servers. Of course, we cannot eliminate everything because after all, we do need to communicate with the database in order for the application to proceed, right? So one standard wisdom in our community in terms of speeding things up is to basically group things into stored procedures. Okay? Push application logic to the server in addition to queries. So in this case, what we might want to do, for instance, is to notice that in this case, this thing prints out something onto the screen, so it has to be on the application server itself. But then for everything else, we can try to group that together into a store procedure and push that over to the database server. And likewise for this, right? Now, just doing this, as our experiment shows, actually decreases latency by 3x. So I mean, that's obvious why that's the case, right? Because we are reducing the number of round trips, right? But notice, as I have pointed out, right? So in this case, this line has to execute on the application server. Okay. So what does that mean? So that means we need to keep track of the ordering, right? Because in this case, this is actually guarded by an if statement. So this line is only executed if the if statement turns out to be true. So in programming language as well, that means we have a control dependency. We have a control dependency of these two lines on this particular if condition. These two lines are only executed depending on the outcome of the if statement. So if we want to do this store procedure approach, we better at the end of this store procedure return whether this is true or not, because otherwise the application does not know whether it should go ahead and print out stuff onto the screen or call another store procedure or database queries, for instance, right? And in addition to that, in order to make this work, we also need to keep track of all these data dependencies. Well, why? Well, notice that in this case, this guy defines a variable that gets used later on if we decide to go back to the application server. So that means at the end of this store procedure, we also need to return the value of this variable and forward it back to the database server, the application server, if we decide to go back to the application server, right? So, okay, so now you think, okay, well, we just need to keep track of all these things when we write the store procedures. Just be a little bit careful, and we should be, fine. We should go ahead and deploy this on the database as store procedures. But then, guess what, right? There's also this problem of multi-tenancy, meaning that the same database server can be shared across with different applications. And in particular, if it is actually under heavy utilization, then if we push all these application logic to the database, it actually is not that beneficial after all. So maybe after all, we should go back to the original version where we just incur all these extra network round trips, and that might actually turns out better, right? So. And imagine doing this kind of thing for millions of lines of code, right? It's just not going to be, manual effort. It's not going to cut it. So to kind of resolve this problem, what we ended up doing is building a new system called Pyxis. And it does two things in particular. One is it automatically store proceduralizes, if you will, database applications and pushes part of the application logic to the database, like what I was showing you earlier. And to target this problem of multi-tenancy, we also adaptively controls the amount of application logic that we want to push based on the current load on the database server. Right? And we're able to do all of these without any programming intervention, meaning that we're able to do it automatically. We somehow partition the program, split things up, and then we can turn it up, and then we can do execute different things differently. So at this point, you're probably thinking of how is this possible, right? How do we actually do this? Well, let me show you how this works. So imagine this is the original application, which has basically some SQL and imperative logic embedded, intertwined. So what we do in Pyxis is that we first we first collect some sort of profile data about the application. And given this profile data, we have an automatic partitioner that takes in the profile data and tries to partition the application into two parts. One part to be executed on the app server and another part to be executed on the database server as stored procedures. Now, during execution, after deployment, I guess, on the database server, these two kind of partitioned application is going to periodically jump back and forth in terms of the application control, and we call that a control transfer. And to facilitate this adaptive property, we actually have a monitoring component on the database server that keeps track of the current load on the database. Now, for instance, in a case where it turns out to be under heavy utilization, our deployment tool will actually automatically switch back to another partitioning. For instance, in this case, we will decide to do the original partitioning, where we go back and forth between the two servers instead. Okay? So how do we do this kind of source code partitioning, right? So we take the original application source code, and then we just process it from beginning to end. Now, as I mentioned to you earlier, we first do a profiling of the application. And we also collect some capabilities in terms of how many cores, or we need a specification of the two servers that we are targeting. Okay? So for instance, in this case, given this piece of code that I've shown you earlier from TVCC, what we would do is we would collect the number of times that each instruction is executed, so to speak. And we use that as part of the profile information, because that is going to guide us in terms of doing the program partitioning. Now, the next step is to basically do the partitioning, and the way that it works is the following. So we basically take the original program and we create what is known as a program dependence graph. So for those of you who might not be familiar with this, so this is basically a simple graph where every node corresponds to a program statement in the original program. And it also keeps track of control flow edges and also data flow edges. So what do I mean? So by control flow edges, we mean there's control dependence between every statement. Then we basically insert an edge. So in this case, for instance, we know that this is the order of the program, and then since this is an if statement, we have control dependencies with these two statements. Okay, so that's control. So this we create this graph, and we basically add edges in this manner. Now, for each node, as it turns out, also has a weight, which will help us decide on the partitioning, and the weight is at this point we're basically just using the counts that we have collected during profiling of the initial application. So Now we also insert a bunch of data flow edges in terms of talking about where data flow from one statement to another. So in this case, for instance, notice that this count variable is used on the second defined in the first statement and used in the second one. So we insert a data flow edge that talks about there's a data dependency between these two statements, and that's and the thing that we're talking about here is this particular variable, and so on and so forth for the rest of the program, right? So we just create all these data flow edges. So this is basically part of the process of creating this program dependence graph. Okay, so we use this graph for partitioning purposes, and in particular, we generate a linear program to solve this problem, where in this case we're trying to minimize this expression here, where it's basically the sum of the edge wages. The edge weights, since each of them represents basically the number of bytes that needs to be transferred should we decide to cut the program in any particular way, right? So in this case, each edge, both data and control, has an indicator variable EI that is set to 1 if we decide to cut the program at that point. And all these, and this goal is basically subjected to a number of constraints, where we say that EI is equal to 1 if we decide to cut the program at that point, and 0 otherwise. Okay? So all of these, we also have an extra final constraint that talks about how is the load on the database, if you will, in terms of the amount of CPU, memory, I/O resources that are available. And we want to say that whatever positioning that we able to come up with better respect this particular budget constraint, because we don't want to push too much stuff to the database, right? So you can imagine we can basically solve this linear program for different values of budget, which corresponds to different values, different amount of resources that is available on the database. And that basically gives us different partitioning of the same program itself. So you can think of this as we just generate various versions of the same program, except that they all differ in terms of how much application logic we decide to push from one server to the another. So solving this program basically gives us a solution where we assign each node, in this case a program statement, to either the application server or the database itself, right? And the output of this program is represented using something called Pyxis, which is sounds like the name of a drug, and I apologize for that name, but it actually stands for the Pyxis Intermediate Language, better or worse. So here's an example. I mean, it looks very much just like Java. In fact, we can actually program in this language. The only difference is that every statement is now annotated with either D, meaning that is intended to be executed on the database, or A, which means it's intended to be executed on the app server. So as I've shown you here, this is just one example. We can obviously generate different type of partitioning given the different budget constraints that we have for the database server. Well, but now we still have the problem, right? I mean, how do we actually compile this thing down to a real program that we can execute? So that's what this compilation and runtime component in Pyxis is all about. So again, we want to somehow compile this program in this funky language into Java. And again, one half of the program is going to be executed on the app server, another half on the database. And I just want to point out that we didn't change anything for in terms of, in this case, it's a Java program. So we just run it on any normal JVM. We don't require any special tricks or any sort of a specialized runtime system in order to deploy this. Meaning that we basically take the program in this pixel representation and we compile it to Java. And you can basically run it anyway, right? Okay, so the compilation procedure is pretty much straightforward, except for two issues. One is how do we actually do these kind of control transfer implementation between the two servers, and also how do we sync up the heap, right? Because as I pointed out, we have all these data dependencies. We somehow need to be able to sync up the two runtimes, if you will. So again, back to this example, right? So how do we do the control transfer, for instance? Well, we simply try to group together statements that have the same annotation. In this case, they are all annotated with database. Okay, so we know that these guys need to be executed on a database. And then, so basically what we do here is we just take these statements, compile them to what we call a code fragment, and then execute them on the database server itself. And then we basically keep doing this until we encounter something that we know has to be executed on the app server. At that point, the runtime system on the two servers will then basically go and tell the other guy, okay, well, I need you to execute this next code fragment, which corresponds to, for instance, code fragment number 110, for instance, so on and so forth for the rest of the program. Well, so that's easy, I mean, relatively speaking. Now for the heap, right, what do we do? Well, so during execution, right, we actually keep track of all the things that, all of these code fragments, I guess. We actually keep track of all the state changes that each of these code fragments incur. So for instance, in the code example that I've shown you, we'll basically note that when we first try to execute this particular code fragment on the database server, our runtime will automatically figure out that we need to forward these two, the values of these two variables over from the app server to the DB server. And that's because they are used inside this particular code fragment. So our runtime system automatically figures all that out. And then it also keeps track of anything that gets changed. For instance, if the runtime actually execute this code fragment on a database server, we'll notice that we actually define the variable credit. So if the if condition turns out to be true, meaning that we do go back to the app server, we would forward it the value that is needed in order to print out the statement onto the screen. And if we decide to stay on the app server, then the database server, then we don't need to forward anything because there's no change to the heap. I mean, it's basically the same heap. So we do all that inside our runtime, which is basically just another Java program that sits on top of the JVM on the two servers. There's nothing special about this. And so on and so forth. So we keep executing that way, right? And again, we have a monitoring component which will basically tune to different loads on the database, right? So if the load on the database turns out to be too much, we'll simply switch to another partitioning that we have pre-generated when we solve the linear program. And then we'll just execute as before. I mean, nothing really changes. It's just basically you can think of this as just running another version of the same program. Okay? So now let's look at how do we actually do in terms of experimental results, right? So in terms of experiment setup, we have a TBCC implementation in Java. In this case, we have 20 terminals, each running simultaneously, issuing new order transactions, the most complicated one out of all of them. And standard machine room setting. And in this case, the database server has 16 core total. And we, along with the one that we automatically generated, we also compare it against two other implementations. The first one being the original application, if you will, where everything is executed using JDBC. So it basically incurs all these network round trips. And another one where we try to manually push everything as much as we can over to the database server. So that's what we call a manual implementation. So with all the cores that are available, well, in the beginning where we did this experiment, we measure the amount of, this is the standard latency versus throughput graph that we are all familiar with. So the JDBC implementation has kind of a high latency as you would expect, and it's also not able to sustain very high throughput numbers because of all these network round trips that have been incurred, right? As compared to the manual implementation, where you can see here it has much better latency and also able to sustain to high throughput because we push most application logic to the database, and the database has a lot of cores that are available to run all these things. Now for us, so we automatically detect that in this case there are plentiful resources that are available on the database server. So we ended up choosing a partition that is very similar to the manual implementation or the store procedurized implementation, where we try to push as much stuff as we can over to the database, and this makes sense, right? So basically, we're able to do this all automatically without the programmer, doing all this manual process of creating all these store procedures and whatnot. So we basically get a 3x latency reduction, and we also get substantial improvement in the throughput. Now, let's take a look at the reverse, right? So in this case, we restrict the number of cores that are available on the database server. So when we did the same experiment, so again, JDBC implementation, does kind of all right, and a stable latency across the board. Now with manual implementation, the interesting thing in this case is that in this case, it's not able to sustain to high throughput numbers because at some point it saturated the entire database server. I mean, there are no more cores available, so it just ended up choking. It's not able to handle all these extra transactions that are coming in. Now, in our case, we're actually able to detect that there are not enough resource available, so we choose a partitioning automatically that is similar to the JDBC implementation. So this again makes sense, right? Because we basically want to use the JDBC implementation if there are not enough resources that are available on the database server. So finally, in this experiment, we did the dynamic switching thing, where in this case, this is x-axis now is time. So we fix a particular number of throughput, and we measure the average latency across the board. The only difference is that at some point in the experiment, we decided to restrict the number of cores that are available to the database server. So initially, it has access to all 16 cores. But at some point into the experiment, we decided to cut some of them off. Okay? So JDBC performs as is, and then in this case, the manual implementation, originally it did really well, right? Because it has all the cores that are available. And at some point after this, kind of shut down, the latency just skyrocketed because of the fact that, once again, a similar case as before, there's no more cores available. Now, for our implementation, the interesting thing is we are able to automatically switch between these partitions. So you notice that in the beginning, we choose a partition that is very similar to the manual implementation, where we push things to the database. And at some point after we shut off most of the cores, we decided to switch automatically over to the JDBC implementation. So just for the record here, we also show the percentage of transactions that are served using the JDBC implementation. So you can see that initially, none of them were using that particular version because there are plenty of resources that are available. But at some time, we gradually converge to this other mode of operation, if you will, where we execute most of the things using this JDBC implementation, right? So in summary, in this case, we're basically able to show that we automatically switch to the most efficient implementation based on what is the current server load on the database. Yes?
For the last 3 points, which have 100%, why is it not the same as the red?
That's just because of measuring the way that we measure latency. It's an average. It's a running average. Yeah. Okay? So that comes to the conclusion of this talk, where I basically show you this umbrella project where we try to use different programming analysis techniques to try to speed things up. So the goal of which is to help application developers write these kind of database applications. So in particular, we show you 2 things. One is the ability to convert things from imperative code into SQL, and another piece of work that is able to do automatic code partitioning and also distribution of the application across the 2 servers. And we have a website if you're interested in learning more. And at this point, I would love to take questions. Thanks.
Part of the talk, how do object-relational mapping systems play into that? Because you're actually generating SQL to run on the server, which of course the ORM would ordinarily do.
Yeah, so in the traditional ORM setting, most of the ORM logic would be on the app server, right? So we haven't done the integration yet, but I think it will be very interesting, where we start pushing part of the ORM code over as store procedures onto the database and see how that will work out. I think that's a very interesting follow-up work. Because
especially for the updates, because they're running in cache, and then they have to somehow take a diff of the updated cache updates and somehow package that up into updates that get sent down to the server. It can be quite inefficient.
Right. So on one aspect, the good news is we already have the machinery for all of these, right? Because we already keep track of the heap and blah, blah, blah. But the interesting thing is perhaps how we formulate the linear program to also take all that stuff into account. So I think that would be an interesting point follow-up work.
So it seems the first part of the talk with the query synthesis. So what you're doing is you're taking an imperative code and you're turning it into a SQL query, right? But then the database afterwards turns the SQL query into imperative code. So can you also think of a way where you can actually take a normal application which does not involve that communication with the database and try to optimize it based on some relational algebra?
So I guess we probably don't want to push things that the database is not good at doing into the database itself, right?
Yeah, no, I'm just saying forget about the database. Just, you're analyzing a program which does any sort of processing of data which does not sit on a database but sits in memory somewhere. And you're just analyzing this program, creating a relational algebra, and then using standard database techniques to optimize this and to create a new code.
So,
can you think of a way of using your work to do this kind of optimizations?
You mean for other contexts, or you mean? Yeah, so yeah, exactly. So in fact, we're looking at using similar techniques for MapReduce programs. So you can think of somehow we're able to, it would be nice if we can come up with a way to convert arbitrary imperative code into Hive or Pig and leverage off the query engine's ability, right? So what database systems are good in doing is basically doing this kind of relational optimization, if you will, right? So it's very good at choosing what is the best query plan and so on and so forth. So from that respect, I don't think we want to go in that direction as to bypass all that machinery. I think it's good that databases are good at doing that. So what we're trying to do here is leverage what they're good at doing, right?
Yeah, that's what I'm saying. You use the existing database technology to create the SQL query and let the database give you a more optimized code on processing the same data.
Yeah.
But not actually communicating with the database, but doing the same thing inside the program that you're running.
So you mean like actually do the reverse, which is we try to push some of the database logic back to the app server? Yeah. Oh yeah, I think that would be interesting. Although I think in some sense having the computation close to the data is a good choice, right?
I'm talking about situations where the data is actually in the application.
Oh, I see. Yeah, sure. Yeah, that would actually be interesting. So I think that would get into some of the work that we're trying to do for MapReduce, for instance, because in that case they do heavily use main memory for at least for temporary storage. So I think the interesting thing in that case would be to model what is how much data that we can imagine will be sitting in the cache, and being able to optimize that way, as opposed to right now we assume that the cache does not exist, or in other words, we assume that most of the data is sitting onto the database and it's not cached on the app server. Yeah, but I think that's a good point. Yeah. Yes.
So one way of specifying the question is if you have expressions in LINQ, which look exactly like SQL, but they're processing arrays and less within the code, right? So we can ask this question. So can you use any of your program analysis tools to kind of improve the performance?
Yeah. So I think that's a good point. So in fact, I think the reverse question is also interesting, which is if we can push things from app server to the database, why not also lift some of these things back from the database over to the app server, right? For cache locality, for instance. I think that's a good point. Yeah. Please.
So I have an example in mind. So for example, I have an application written, and what it is doing is it's selecting two tables, like doing a select star on two tables A and B, and then within the application logic, it's trying to do something with those data, and also it has an extra parameter, say X. Now, if we want to convert this to a SQL query, every time you'll have to write a new query depending on that parameter, right? But in the previous case, it was doing select star on A and B, which is more efficient in terms of using the database cache. So probably those two expressions would be cached, and it would be very fast. And the further processing is being done in the memory, so it would be very efficient. But in your approach, it will be writing a new SQL query depending on that parameter, and it won't be cached in the database. So don't you think in that case the performance might vary quite a bit?
Yeah, I think that's a good case actually. Yeah. Thanks for bringing. Yeah, I think absolutely. Yeah, I think that would be an interesting thing to look at. It's just that at some point the linear program starts to get really unwillingly in terms of being able to solve. So it's just all about how much tricks we can pull in terms of being able to formulate a very small program that is able to solve it. Yeah. Cool.
Thanks again.
Thanks.